Hello, I'm Roberta Crapanzano, a PhD student in nanotechnologies and material science at the University of Milano Bicocca. This talk is focused on the investigation of zinc oxide luminescence, which is strongly affected by the material point defects type and concentration. In particular, I will analyze the impact of morphology and growth condition on zinc oxide final defectiveness and hence on its optical properties. This study was performed at the University of Milano Bicocca by the joint effort of all the Irene mentioned scientists. Zinc oxide is a wide bandgap luminescent semiconductor whose applications span from photonic and electronic devices to gas sensor and biomedical agent. Zinc oxide luminescence typically display an UV excitonic peak and several bands in the visible region of the spectrum due to the presence in its forbidden energy gap of several defect species. Anyway, the origin of these defect bands is still under debate in the literature. To address the complex zinc oxide luminescence, our group developed a systematic experimental approach. 6 different zinc oxide specimens with dimensions ranging from the bulk to the nano-size were studied exploiting 3 different spectroscopical techniques. This analysis enabled us to evidence and discriminate the role of excitation energy, dimensionality, and growth condition on zinc oxide optical properties. First, I will present you in detail the 6 specimens and the mechanism underlying the use of spectroscopical techniques, and then I will analyze the result of this optical investigation. The 6 zinc oxide specimens include 4 nanoparticles synthesized by our group, and macrometric powders and a bulk single crystal purchased from outside companies. In particular, regarding the nanometric sample, we studied 2 bare nanoparticles of diameter of 22 and 5 nanometers respectively and grown by hot injection method. Moreover, we studied 2 zinc oxide nanoparticles of 5 nanometer diameter supported onto 8 spherical or rod-like silica nanoparticles and grown by sol gel procedure. The used spectroscopical technique, radioluminescence and photoluminescence, exploit 2 different excitation sources, ionizing radiation and light respectively. In radioluminescence, the excitation is not selective and involves core state. In fact, when an X-ray photon is absorbed, its high energy is converted into a cascade of electron-hole pairs, which finally thermalize in the conduction and valence band respectively. Then the free carriers can migrate in the material, and several different relaxation pathways can occur. For example, they can be trapped by trap layers, or they can recombine on a luminescent center. The transport and luminescence steps of radioluminescence can be further investigated performing radioluminescence measurements as a function of the temperature. On the other hand, in photoluminescence, it is possible to selectively exit transition between the delocalized band or between intragap states. Hence, the decay time of a certain emission band can be studied. The room temperature radioluminescence spectra of all the samples disclose different luminescence features. A Gaussian reconstruction of all the samples, anyway, disclosed the occurrence of a maximum of 5 emission bands throughout all the samples. These 5 bands comprise 4 visible defect-rated spectral components and an UV excitonic peak. The same 5 emission bands were identified in the radioluminescence spectra recorded as a function of the temperature, even if their relative intensities change with the temperature. In fact, it is known that the decrease of radioluminescence intensity when the temperature is increased is due to thermal quenching. but the activation energies of this phenomenon, and hence the temperature at which it is observed, depend on the emission species. We tentatively estimate the activation energy of the spectral components. For all the specimens, the activation energy of the excitonic peak results of about 40 mV, in rough agreement with the literature, while the activation energy for the most emissive bands of the nanometric samples results of about tens of millielectron-volt. To evaluate the role of excitation energy, all the specimens were excited exploiting X-rays photons of mean energy of about 6-7 keV, UV photons with energy higher than zinc oxide band gap, and visible photons with energy lower than zinc oxide energy gap. The radioluminescence and photoluminescence spectra recorded above zinc oxide energy gap disclose a general similarity, despite the different excitation and relaxation mechanism involved. The greatest difference is the intensity of the excitonic peak, which is boosted under ionizing radiation. This result can be due to the enormous number of carriers generated in radioluminescence mechanism, while in photoluminescence, one absorbed photon generates only one electron-hole pair, leading to a lower probability of exciton recombination. Exciting below zinc oxide energy gap, an enhancement of the green and blue bands is observed, especially in nanoparticles. This result is due to the possibility of directly excite intragap state when the energy of the excitation is lower than zinc oxide energy gap. Hence, it is possible that the intragap states which are directly excited have a higher probability of radiative recombination. To study the role of dimensionality, we will focus on the absolute radioluminescence amplitude. The overall emissions of the nanoparticles are about 1-2 orders of magnitude smaller than those of the macrometric powders and the bulk single crystal. Moreover, the exciton defect emission ratio decreases as the size scales down. These results suggest that the degree of defectiveness is higher in macrometric samples with respect to that of the bigger ones. In fact, as the size scales down, the surface-to-volume ratio increases. Hence, a higher number of lattice size is exposed. Since interfaces create disorder, the formation of point defects or surface defects such as dangling bonds is favored. Moreover, the smaller is the material size, the higher is the probability that the excitations reach the surface and interact with its defect states. Consequently, in nanoparticles, the generated excitons recombine preferentially on the surface. This recombination can be radiative with the emission of a phonon or non-radiative with the dissipation of the energy by heat. Anyway, the decrease of the radioluminescence intensity observed in the nanometric systems suggests that non-radiative recombination is boosted in nano-sized materials. This result is further validated by time-resolved photoluminescence measurement. In fact, when an additional quenching channel is present, a decrease in the time decay is observed. Comparing the time decays of the same emission band of a nanometric sample and of the macrometric powders, it is possible to notice that the decay time of the nanometric sample is 2 orders of magnitude smaller than the one of the macrometric powder. others. To examine the role of growth condition, we will focus only on the 4 nanoparticles. In particular, I recall that the 2 bare nanoparticles are grown by hot injection method, while the 2 silica-supported nanoparticles are grown by sol gel procedure. First of all, nanoparticles synthesized by the same procedure route display the same emission band that have also a similar radioluminescent efficiency. Moreover, the decay times of the same bands of nanoparticles grown by the same synthesis are of the same order of magnitude. In particular, for the bare nanoparticles, the decay times are the same, while for the silica-supported nanoparticles, a slight difference is observed. This difference can be due to the different morphologies of the silica substrate, that in one case is spherical, while in the other is rod-like. Possibly, the morphology of the substrate influences the surface properties of zinc oxide nanoparticles, leading to a different defectiveness and hence to a slight differences in the optical properties. In conclusion, this work highlighted the occurrence of an UV excitonic peak accompanied by 4 defect-related visible bands throughout several zinc oxide specimens with different morphologies, unveiling the presence of the same defect species. Anyway, the relative concentration of polluted defects vary with the size and the growth condition, leading to a different colored light output as the chromaticity diagram shows. Each point of the diagram represents the overall shade of color that zinc oxide specimens emit under X-ray excitations. Moreover, the relative intensity of the bands depends on the excitation energies. Hence, this accurate investigation paves the way for controlling zinc oxide optical properties, choosing shapes, dimensions, and interfaces, leading to the possibility of engineering zinc oxide luminescence for optical devices. I would like to thank you all for the attention and thank my colleagues for their work and support. Any questions in the comments below this video will be very appreciated. Thank you.